In this lesson, we'll learn about proof by exhaustion. A proof is a logical argument to show that a mathematical statement is always true. For example, I might be asked to prove that all multiples of 2 are even numbers. These are basic proofs that have already been proven. We can use that to prove further things. So we can use the fact that all multiples of 2 are even numbers when we are asked to prove something more complex. Now, exhaustion means to break the problem down into smaller bits and proving the statement for all types of possibilities. For example, I might be able to break the proof down for even numbers and odd numbers and show that for even numbers the statement holds true and for odd numbers the statement holds true. So it must hold true for all integers. We can go a step further for proof by exhaustion and break down every single possibility. So an example of this would be that all odd integers between 2 and 8 is a prime number. Since we have a limited number of values, I can just show each case individually. So for 3 is a prime number, 5 is a prime number, 7 is a prime number. So these are the 3 odd numbers between 2 and 8 and they are all prime. In this case, I broke down the statement into all of its possibilities and then showed them individually. So I showed that 3 is a prime number at first, then showed that 5 is a prime number and 7 is a prime number. So I broke down all the possibilities and then showed that the statement holds for all of them. So this is exhaustion. In AS Maths, we learned another method about deduction. For deduction, we have to solve the statement or show the statement is true using basic facts such as 2 plus 2 is 4 or all multiples of 2 are even numbers. So we take known facts like this and use that to prove other things mathematically. In exhaustion, we break down each case or we break down the cases into odd and even numbers. So we can be asked to prove that all cube numbers are a multiple of 9 or one more or less than a multiple of 9. Now for this case, I can show the case for multiples of 3, since 3 is the prime factor of 9. I can show the case for multiples of 3, one more than the multiple of 3 and one less than or two more than a multiple of 3. 3n minus 2 and 3n minus 1 are basically the same. So if I draw a number line, it will be clear. So this is 3, 4, 5 and 6. 2 more than a multiple of 3 is 5. But 6 is also a multiple of 3. So 5 can also be written as the multiple of 3. So 6 over here minus 1. So it's the same. I'll use this 3. So if I cube 3n, I get 27n cube. I can factor this out. I can write this down as 9 times 3n cube. So this must be a multiple of 9. For the next case, we have this cubed. So this will be 3n plus 1 times 3n plus 1 whole square. This is equal to 3n plus 1 times 9n square plus 6n plus 1. This would be 27n cube plus 18n square plus 3n plus 9n square plus 6n plus 1 This will be 27n cube plus 27n square plus 9n plus 1. This part over here can be factored, 9 can be factored out from that, so we can take 9 common, write down 3n square plus 3n plus 1. This part over here must be a multiple of 9, so if I add 1 to it, this is 1 more than a multiple of 9. Now for the third case, where it's 2 more than a multiple of 3, I'll break this down similarly. So 3n plus 2 times 3n plus 2 whole square. This would be 3n plus 2 times 9n square plus 2 times 3 times 2, which is 12n plus 4. From here I get 27n cube plus 36n square plus 12n plus 18n square plus 24n plus 8. This would be 27n cube plus 54n square plus 36n plus 8. This must be a multiple of 9, and if I add 8, this will be 1 less than a multiple of 9. If I want to say it that way, I can just write 8 down as 9 minus 1. Now this whole term can be factored out, 9 can be factored out from here. I can write this down as 9 times 3n square plus 6n plus 4n, 6n square plus 4n plus 1 minus 1. So this part over here is a multiple of 9, and we have a minus 1, so this is 1 less than a multiple of 9. Now in this topic we have to learn about something new, which is a counter example. A counter example is used for the opposite. So we were proving things so far, now we'll be disproving things. Counter examples are one of the best ways to disprove things. It's one of the simplest ways as well. So if there is a given statement, all I need to do to disprove it is find one example that goes against it. So for example, if I am said that the sum of two consecutive prime numbers are always even, I have to find only one exception to this to disprove the whole conjecture or statement. For this I can find example 2, 3. So the first two prime numbers are 2 and 3. If I add them together, I get 5. This is odd. So we have disproven our theory or disproven the statement. So all proof related questions, if we are proving something or disproving something, we always have to write the final statement down. So for example, we had the 3 cases mentioned over here. For this we had a multiple of 9, for this we had 1 more than, and for this case over here we had 1 less than a multiple of 9. So for a final statement, I'll just write down that all cube numbers are multiples of 9 or 1 more or less than a multiple of 9. And for counter example, so for cube numbers we give this statement, or for any proof we give a statement like this where we paraphrase the question statement. And for a counter example we just say that so the statement is not true. Our final statement is important for proof questions. A question that would include both concepts would be this. So this question over here, this question contains two parts. One of them is that 3 consecutive even numbers is always a multiple of 2. So we have to prove that at first, and then we have to use a counter example to show that it is not always a multiple of 4. So if the first even number is 2k, the next one will be 2k plus 2, and the third one will be 2k plus 4. So 2k plus 2k plus 2 plus 2k plus 4 is the sum of the 3 numbers. If I find this will come out to be 1 2 3 4 5 6k plus 6. So I can take 2 common from here and write down 3k plus 3. So this is a multiple of 2. This must be even. We don't have to prove that. Now we have to show that it's not always a multiple of 4. Now for this I'll have to find a counter example. For finding a counter example, there isn't a trick, we just have to manually do it. If I consider k is equal to 1, we get 2, 4 and 6. If I add them together, 2 plus 4 plus 6 is 12. This is a multiple of 4, so this isn't our counter example. We have to find something else. If k is equal to 2, we get 4, 6 and 8. If I add them up, we get 18. This works as an example. 18 divided by 18 is not a multiple of 4. If I look at the times table of 4, we get 4, 8, 12, 16, 20. 18 isn't over here. This isn't a multiple of 4. And finally, we'll just write down a statement by paraphrasing the question, like therefore. So this is the first part of our statement, that the sum of 3 consecutive even numbers is always a multiple of 2. The next part will involve stating that it's not necessarily a multiple of 4. And this is it for this video.